One of the most common representations for solid models is constructive solid geometry, or CSG for short. CSG combines simple shapes known as half-spaces into complex shapes using Boolean operations, such as union, intersection, and difference. However, CSG also has several limitations. First, it cannot express all shapes formed by the half-spaces, such as the yellow heart shape here, even though the boundary of the heart shape coming from either of the two half-spaces. It is impossible to express it using CSG operations on A and B alone. One would have to add a new half-space, such as C, to express the heart as a more complex Boolean expression. Constructing the additional half-space like C is challenging for both interactive design and reverse engineering, because it does not contribute to the geometry of the final shape. Another drawback of CSG is that Boolean expression can be very complex, even for simple shapes. For example, the simple Adobe logo consists of only 10 linear half-spaces. Its Boolean expression is not so simple. Furthermore, the same shape can often be represented by multiple but drastically different Boolean expressions. Finding an easy-to-edit Boolean expression that reproduces a given shape remains a key challenge in reverse engineering of CSG representations. To address the aforementioned limitation of CSG, we propose a new representation to model solid from half-spaces. Our representation do not require hidden half-spaces. It is intuitive and lightweight, and it is also suitable for reverse engineering. Similar to CSG, our representation uses a set of half-spaces. But instead of Boolean operations, we define the shape using a set of sample points lining on the half-space boundaries. The idea is to use these samples to indicate which part of the half-space boundary belongs to the boundary of the final solid shape. Our shape, which we call boundary sampled half-spaces, or BSH for short, is defined as the set of input half-space boundaries that form a solid shape. While there are many such possible shapes, we require the BSH shape to preserve the half-space orientation, contain as many samples as possible, have the least boundary lengths in 2D or the least area in 3D. Lastly, we also require the output to be sample connected to avoid artifacts such as corner cutting caused by encouraging a compact shape. Please see the full presentation for details about sample connectedness. The BSH shape, according to this definition, can be computed using state space search algorithm that iteratively perform graph cut on the dual graph of the half-space boundaries. We give a more detailed account of the algorithm in the full presentation. An important property of BSH, which we prove in the paper, is that it can describe any shape using only half-spaces that bounds the shape and a sufficient number of samples. Without the need of hidden half-spaces, BSH is more convenient than CSG for interactive design and reverse engineering. Even for shapes that can be expressed by CSG without hidden half-spaces, BSH is often a more compact representation. For example, this simple Adobe logo can be represented by BSH using only 11 sample points. But CSG would need a much more complex Boolean expression, which is not easy for user to understand or edit. It is rather straightforward to convert another shape representation, such as a mesh, into BSH. One can extract a set of half-spaces using existing mesh segmentation and half-space fitting algorithms. The sample points can then be gathered on the fitted half-spaces using a simple heuristic that we describe in the paper. This example compares the editability of the result of reverse engineering for CSG and BSH, starting from the same set of half-spaces. Although the shape can be obtained by a relatively simple sequence of Boolean operations from tori, planes, and cylinders, applying a state-of-the-art algorithm for inverse CSG produces a Boolean hierarchy that contains many counterintuitive operations, making it difficult for user to perform additional editing operation on this shape. In contrast, by converting the input to BSH, we can easily modify the shape, such as removing some rings and a shelf. We conclude with a live interactive editing session for this vase shape converted from a mesh input, showing removal, addition, and modification of half-spaces and samples. Throughout the process, the user does not need to keep track of additional data structures, such as a Boolean expression, and the shape maintains a solid. Please check out video, code, program, and more at the following URL. Thank you.